Let me just start my PowerPoint. So I hope you can see it. So yeah, as it was already mentioned, today I'll talk mostly about cavitation, and that's bubbles basically, which have some relation to space science and engineering, as you will see, but also other stuff. So it won't be directly related to microgravity research, although some of the experiments that I will show were actually done in microgravity. So hopefully this will be also interesting for you. So what's cavitation? Let's start with this, right? So cavitation is basically something very, very similar to boiling. So everybody knows that you can boil water if you increase its temperature. Let me just use this. If you increase the temperature from, let's say, 20 degrees at 1 bar normal pressure, and if you increase this temperature to 100 degrees, the water will boil. You will get vapor, right? But there is a second way how to get to vapor, and this is if you leave the temperature the way it is, let's say 20 degrees, but you decrease the pressure down to about 2000 pascals. So it's a very, very low pressure. And essentially the same thing will happen. This you can also see in these two movies. The one above, this is normal boiling at 100 degrees Celsius and normal pressure. And the one below, this is cavitation. But you can see I can hold this flask in my hand because it's not hot, it's 20 degrees, but I vacuumed air out, right? So you have very, very low pressure inside here, and you have bubbles boiling. It looks like boiling, but it's called cavitation. So what's so special about cavitation? What is special is that when it happens very, very quickly. So this is a nice experiment, which I don't recommend doing at home. You take a bottle and you drink the beer first, and then you fill it up almost to the top with water, and after that you hit the neck of the bottle, and if you hit it hard enough, what happens, the bottle's bottom will fall off, right? So it doesn't seem very special to break a bottle, but once you look at this at a very high speed recording, this is now 200 times slowed down. The bottom of this flask, you can see bubbles appeared and they disappeared, and at that moment when they disappear, the bottle breaks, right? So what's interesting here is that this when we hit the bottle, actually what happens, we create a shock wave, and as it reflects at the bottom of the bottle, you get a negative pressure. The pressure goes below this 2,300 something pascals. You get bubbles, and when the pressure recuperates to a higher pressure, the bubbles disappear, they implode, we call it. And this implosion basically is so violent that the bottle cannot stand it and it breaks, right? And this happens really, really fast, right? So we can go even one step further to check out what is going on in more detail. And these are the experiments that I've mentioned before, done in zero-G. This was done actually in Switzerland at APFL by Uti Soponen, and she's now actually at ETH as a professor. And what they've done here, what they wanted to do is they wanted to make a very, very spherical bubble. It's very hard to make a bubble which is almost perfect. And to make it perfect, you need to take away all the disturbances. And one of the disturbances, such as walls and free surfaces and so on, and one of the disturbances is also gravity, right? So that's why they decided to go into the airplane and then fly the parabolas and do the experiments there. So what we're looking at now is, I think that's about 300,000 frames per second. So it's about 10,000 times slowed down normal recording. And you can see how the bubble grows. So it grows, I think this one is about 3 millimeters in diameter. So it's a very, very small, tiny bubble, what we're seeing here. So the growth itself is not that exciting, I would say. But what happens after it reaches this highest size, this is when things start to get violent, let's call it. So now the bubble starts to collapse, and you can see it, it's much faster phenomenon, right? It goes faster, 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 up to a point when even 300,000 frames per second is just not enough. So at that point, we need to speed our observation even more to about 10 million frames per second. So this is now at, I think, 10 million frames per second. And as you can see, the bubble shrinks even further, basically to a point, right? You can do this only because you're doing this in 0G. It's very hard to do this in normal gravity. In normal gravity, you will always have some geometrical disturbance. And what happens at this point when it's stopped right now, you can see this white spot happening here. These are actually the gases which could not escape the bubble because the shrinkage of the bubble was so fast, the gas inside could not escape. Because of that, it gets compressed and gets compressed to a gigapascal level. So thousands of bars we are talking here, right? And because of these high pressures, we have very high temperatures, and the very high temperatures in what we're looking at here, you can actually measure them. They're in the range of about 10,000 degrees Celsius, right? So it's a huge temperature peak, but very local one, right? So you don't get burned if you have your hand nearby, but locally you have very high pressures and temperatures. And this white spot here, it's called sonoluminescence, when the gases, due to these two parameters, basically emit light. So, and through this light, you can calculate what was the pressure and the temperatures in there, right? So after that, what happens after that? We have a shock wave, a really beautiful spherical one, and this ring which you saw spreading around, right? This actually traveled at about 1,500 meters per second, right? So it's 3 times faster. The speed of sound in water is about 5 times faster than the speed of sound in air. So it's an enormous velocity that you can see. And this shock wave, which travels around, this is the thing that basically destroys at the bottom that I've shown you before, right? So it's quite a violent phenomenon. So that was just one bubble, right? So we're talking clouds of bubbles, many bubbles, right? And how do we get from one bubble, from a very clean experiment, to a dirty experiment with many bubbles which interact between each other and so on? So one way to do it is by the Bernoulli effect, right? So Bernoulli effect is basically telling you that if you speed up the flow, what happens, you need to, if the flow speeds up, locally, the pressure will drop. And if the pressure drops a lot, right, again, below this vapor pressure, we call it here, water will cavitate, or any kind of liquid. So one way to if you want to do the experiment about the Bernoulli effect, the simplest one is just taking two sheets of paper and blowing in between them, and counterintuitively, the sheets of paper will move closer together. And this is because the pressure between them gets lower, right? So the pressure outside basically squeezes the 2 sheets of paper together. That's the Bernoulli effect, right? So how does this look in real application? We have a nozzle here, and the flow goes from left to the right, and it's squeezed through this very tiny nozzle here. So when it's squeezed, it speeds up. Because it speeds up, the pressure drops, and because the pressure drops, we get bubbles. And this white fog here, actually, this is with a normal cell phone camera. These are actually bubbles traveling at about 40 meters per second. So it's about 120 kilometers per hour. So it's quite fast. But if you want to see what is actually going on in here, again, we have to use high-speed cameras to check out the dynamics inside. And you can see it, well, we call it, it's a very rich dynamics. We have a sort of attached cavitation cloud, which then separates. This is a separate, it's many movies together. It separates, and these clouds collapse again. And when they collapse, you can see this red stuff that is also there. These are actually the measurements of these shock waves that I was talking about before. They're not as nice as the one before, because here we're talking about clouds of bubbles, thousands of bubbles collapsing, not exactly at the same time, not exactly symmetrically, and so on. But these still have an amplitude of a couple, maybe 100 bars or so. And they can travel what you're seeing here at the velocity of about 300 to 700 meters per second. So not quite the speed of sound in clean water, because you have so many bubbles in there, the speed of sound is a little bit slower. but it's still fast, right? And how else the bubbles look like, right? So if you imagine, I was talking about the Bernoulli effect before. So for example, if you have a wing of the airplane, one of the effects of the lift is that you have lower pressure on the upper side and higher pressure on the lower side, right, of the plane. And this makes the plane basically fly, let's go. And if you would put this kind of wing underwater and move it very rapidly, what would happen? Pressure on the upper side would get lower. And because of that, maybe cavitation can appear. Now, if you put this kind of wing and rotate it, what you get is a propeller. And again, this is, for example, a ship's propeller, which rotates, and on the side, which has a lower pressure, you will build up bubbles, and these bubbles will, cavitation bubbles, they will appear and they will collapse and they will cause all kind of trouble, right? So this would be a propeller, for example, and this one here is actually beneath, this is a water turbine. So you can have some kind of a cavitating rope of bubbles, let's call it. These two bottom ones, these are maybe a little bit more exciting, let's call them. This is the liquid oxygen pump of Space Shuttle engine, one of the three main engines. And again, you can see it cavitates, right? So this would be pumping oxygen into the rocket engine, right? And the conditions in there are so extreme that basically you cannot avoid cavitation in there. And a similar thing here, a little bit more modern one. This is the oxygen pump of the Vinci motor, so of the new Vega rocket, and also of the ESA Vega rocket, and of the second stage of the Ariane 6 rocket. Right? So this is what is happening in there. So again, you'll have cavitation going on in these pumps. Why is it so important to study cavitation? Yeah, because it causes trouble. And one of the biggest problems that you have is cavitation erosion. So it causes also vibration and noise and so on, but in rocket science, rocket engineering, that's not so important, noise, for example, but erosion is, right? So cavitation erosion, there's a couple of examples here. So this would be a water turbine, how it got damaged after hours and hours of operation, right? This would be a valve, again, after hours of operation. This is a rudder of the ship. So ships are particularly funny thing because cavitation on a ship's propeller is not that annoying. If I just go one slide back, if this would be a ship's propeller, you would see that bubbles are created on the propeller, and then they flow downstream, but downstream you'll have the rudder of the ship. And on the rudder of the ship, the pressure is a little bit higher, and the bubbles implode in this region, and they damage the ship's rudder. So that there were occasions that the ship would lose the rudder after just one day of operation, right? Because there was so much erosion on it that it just fell down because of so much damage. And again, okay, this is one propeller here, how it can get also damaged. Okay, so here I have a nice example how violent this phenomenon can be. This is actually Glen Dam. It's very similar to the one, the Hoover Dam, which is maybe more known one. And there's one thing that can happen here. As a precaution, if the water behind the dam would get too high, if there would be a lot of precipitation, right? What they would need to do is they would need to channel the water from behind the dam around it through pipes, not to damage the turbines beneath it or the dam, right? And this is how this pipe looks like. So the dam would be here on the right side, so it would flow into this bucket here and then through these pipes and go beneath the dam. And the first time they ever used this was in the 80s, I think, of the last century. This is what happened within a couple of hours. So this is inside this pump. And what you can see is actually cavitation damage, which happened within a couple of hours. These are people here. So you can imagine this is a hole which is about 40 meters long, I think, just in a couple of hours, and bubbles did this, right? So it's crazy how violent this thing can be. Okay. So I have another example. So just to do your own experiment, I call it hand decavitation. This is actually what is going on in your fingers. So I can try it if I do this. Almost nobody likes this sound, right? Popping sound. Actually, what is going on, this is a CT scan of your one's hand. And when you pull the finger, you will see a white spot here, and it disappears. And actually what you do when you pull the finger, you increase the volume in your joint, the pressure drops, a bubble is created, and then it collapses, and this pop that you hear is actually cavitation bubble which imploded inside your joint. Right? So don't do that. It's not a good thing to do, especially when you saw what else can these bubbles do. So I had one lecture once when the whole audience did this at the same time. It was really nasty to hear. Okay, let's move to rockets, because I figured that if you're into microgravity research, you like rockets. So let's talk, how are bubbles important for the rockets? So this is the field that I was working on for about 7 years. And I'm showing here two rockets. One is the Japanese H2 rocket, and the second one is the new SpaceX Falcon Heavy rocket, and they both have issues with bubbles, and so it's kind of, I'll try to explain it on these two examples what is going on. So first of all, okay, how does the rocket engine work, right? That's the first thing that we have to clear. So I've just copied this from a really nice book, Thing Explainer, which explains everything really simply. We'll have to go a little bit more detail because it just says lots of fire comes out here. But how do you get to the fire? That's the tricky part, right? What do you need to do to get to the fire which pushes your rocket to the space? So it's actually simple, let's call it. So this would be the Vulcan engine, the first generation, which was used in the Ariane 5 rocket. And what do you do? So you need two things, right? You need the fuel, which is, in the case of Ariane rocket, it's liquid hydrogen. And because there's no air in space, you need to also bring some of the oxygen with you, right? So what you do, you mix these two things in the chamber, you light them up, and you get fire, and rocket goes up. The problem is how to get these two fuels, these two liquids into the rocket chamber, engine chamber. And what you do is you use pumps. So you have a pump here, so this would be a turbopump, and we call it turbopump because what happens is you push the liquid into the chamber, right? Both liquids, they ignite, and after they ignite, or this is a different type, after they ignite, some of the exhaust, which is created at ignition, is actually let away from this main exhaust and passes a turbine. That's why it's called the turbine pump, and this turbine drives the pump, right? So it's kind of a closed circuit. So you use the pump to pump the liquid and oxidizer, they ignite, and the fumes from that run the turbine, and the turbine runs the pump, right? So this is it's a closed loop, which has to be closed really quickly in order to start the rocket, right? But this is the way this is done. So I'm not sure. So this would be maybe in this image here, this would be the pump. I'm not sure which one it is. I think it's the hydrogen pump. And this is this exhaust. This is this pipe here would be this pipe here, right? So this is basically what is bringing your fuel into the chamber here. Now, the trick here is you need to bring a lot of fuel inside the rocket, right? Into the engine. Otherwise, it doesn't work. It doesn't go up. So a lot means, I think, for the liquid oxygen, I can tell you that one. Some of the data is not completely freely available, but we're talking about a couple of 100 kilograms per second, right? And in order to do that, these pumps need to rotate at a crazy speed. Right? The speed of this rotation it's about 40,000, 50,000, 60,000 revolutions per minute. So this means that it rotates 1,000 times every second to achieve this flow rate into and the pressure that it needs to build inside the chamber here. So it's really crazy. And the craziest thing I think is in order to close this route, to bring the fuel into the chamber and then to make exhaust, to run the turbine, which runs the pump, right? To do this, you need to start the pump from not moving to full speed of 1,000 revolutions every second in just one revolution, right? So it's standing still here, and then it makes one revolution, and it's going at 1,000 revolutions per second. Right? If you don't achieve that, the pump won't start, the engine won't start. It will just blow a little bit of fire out, and then it will shut down. Right? So it's really, really, really hard to start this kind of engine. And so that's kind of important for the later story. So how does it look like? A little bit more in detail. So basically, the design did not change a lot since the first, let's call it a real rocket, the V2 from Germany, right? They have the oxidizer pump, and I think this was the alcohol one. I'm not sure what they do, and this is the turbine in between them, right? So it's a very similar design. They just had one turbine which drove both pumps, the oxidizer and the fuel pump. And in Ariane 5, from now, what, 20 years ago, it's basically the same thing, right? You have, this is called the inducer. It's the first part of the pump. This is the real pump. This is what is building up the pressure. And then this part here, this is where the gases come back inside. So the fuel goes, or the fuel, this is hydrogen, fuel goes out somewhere here, and here is where the exhaust comes in and drives this pump, and this turbine, and this turbine then drives the pump and the inducer. Basically, it's the same design as it was almost 100 years ago, right? The trick here is that this part here, the upper part here, is used just to increase the pressure a little bit so that this pump here does not cavitate. Because if this pump here would cavitate, if the bubbles would appear in this pump here, it would not bring enough fuel into the chamber of the engine, and the rocket won't fly, right? So what you do, you basically sacrifice this first part of the pump, the inducer, and you have always bubbles in here, and this is what I've shown you before. And you just let it be. You cannot get rid of it. It's designed in a way that it can sustain cavitation for a couple of minutes. After 3, 4, 5 minutes, basically this inducer is damaged beyond any repair, but this is just enough time to fill up, to pump the whole tank of the rocket so it can fly into the space, right? So it's really an optimum design. So this is how it looks like. These are the tests which were done, I think, in Grenoble, maybe in Lille, I'm not sure. And this is this inducer. This is essential. How do you design this part so that cavitation will appear here? It will damage it, but not within the first couple of minutes. So it lasts long enough to pump the whole fuel from the reservoirs. And now we come to the H2 rocket from Japan, which had just this problem. What happened is there was a big failure from this rocket. This was actually the last flight of this rocket. After this rocket failed with satellites which were worth a couple of $100 million, I think, at that time, they just stopped working on this particular rocket. This is the chamber, the upper part of the chamber, which was evacuated from the sea. It was at the bottom of the sea. And what they found is the inducer. And you can see the inducer of this turbopump is damaged. So it's damaged so much within a couple of minutes that it didn't pump enough fuel into the rocket chamber, engine chamber. because there was not enough fuel inside, there was not enough exhaust. Because there was not enough exhaust, the turbine could not drive the pump stops. There was even less fuel coming in, and basically the rocket just fell to the ground, right? So it's a very, very important lecture that people learned at that time. Okay, and this is me actually working on the two inducers for the Ariane 5 rocket. So this is both in Lille. So this is the inducer that was used in Ariane 5, and in Ariane 6 they have a new inducer, and they still don't want me to show the design around, so I just blurred it out. But it's very, very similar to the one that I'm holding in the other hand, in the other picture. So this is how it looks like, and it's made out of titanium alloy for this case, and for the liquid oxygen, it's made out of aluminum usually. So you have to be. You really need to, at this kind of revolutions, you need to be careful about the weight and so on. So usually use titanium or aluminum for this. Okay, so if we go now a little bit to the future, to SpaceX and stuff, what did they do? So they've done a genius trick, right? They're landing their rocket with rocket engines. So this would go up. This is the launch when they put a car inside, if you remember. I don't want to go into discussion if that was smart or not, but okay. So they launched a car towards Mars. And what happened then is they land these three boosters. So the two separate, the side ones and the middle one, they landed with the rocket engine, right? So that's kind of crazy that they're able to do that, right? But the funny thing is, landing, make it stable to land like this. That's not. I mean, it's hard, but it's not impossibly hard. I mean, in even at our university, I learned this in maybe 6th semesters of the study, how to program stuff like this, how to balance something like this. The hard part is getting the engines to lead up again, right? So you use them to go to space, then you shut them off, and after that you light them up again and you land with them. That's the hard part, lighting these engines up, because you have to close this loop, as I've told you, within one revolution of the inducer, and that's hard, and that's very, very, very harsh to do that. Okay, so this is just again the same thing that I've explained to you again, right? So you fly to space, and then these two boosters, right? They fall down to ground, but they just before they land, they light up the engines again, and they land safely. And the third one lands at the sea, actually, on the sea platform. I'm sure you know about that. Now that's one thing what they do, and that's one genius trick that they do. They have some problems in it. The other thing is what they're doing, but that nobody really realizes it, because they have cavitation in there. There's a big problem with cavitation. What they're doing is they're subcooling liquid oxygen and liquid hydrogen. No, they're not using hydrogen. They're using kerosene in this case. But they're subcooling it. Basically, if the liquid oxygen liquidizes at 180 degrees below zero, they go to 190 degrees below zero or so. And with this, liquid oxygen is a little bit denser, which means that the tank can be a little bit smaller, and they save weight with this. So that's one trick they do. But the second trick they do is basically, if you have a lower temperature, you would move this point a little bit to the left, which means that cavitation will occur a little bit later, right? So you can drive your pumps a little bit faster. And because of that, they can be a little bit smaller, and again, you're saving weight, right? So they're really, really, really pushing it at this point, right? Because this is also why they're fueling up the rockets just a couple of minutes before the launch, because once they're fueled, the liquid starts to heat up, it starts to expand, and this is basically the same thing as if there's an astronaut up there, he's basically sitting on a pressure cooker and hoping that it would not explode before they launch it. Right? So they're really pushing the envelope in this case. but this is why this is very efficient and very cheap to go to space this way. But as I said, they still have problems, right? And they being Americans, they deal with it very, very interesting. Like they say, it's a small hiccup because the time that they launched the car into space, right? These two rockets landed perfectly, but the third one crashed, right? And it crashed because they said they failed to light 2 of the 3 engines during the landing burn, right? So it uses 3 engines to land, and 2 of those could not be started, right? And they could not be started because this startup of the rocket engine is so incredibly hard to do, because it has to start rotating at such an enormous acceleration, right? So I was once in France at this kind of test when they tried to see if the pump will do this fast startup. It was a model test, it was not the real one. But once they started, this is a test rig which was about 10 meters long. And when they started, it jumps for about 1 meter into the air. And then they say, okay, successful, let's move on, right? It's so incredibly intense, this fast startup. And the same thing, which is kind of interesting, is what is going on right now, right? With the new rocket that they're using, the Starship, right? I've put this nice image here. This is, I think, Starship number 9, which exploded, and this is the Starship number 10, which is anxiously waiting its turn. And I think Starship 10 actually was then successful for the first time. And I'm showing you here now one movie. Yeah, so that's one thing that the people from USA would say at every explosion. They would say we have lots of good data. That's true, but I'm sure they would be much happier if it would work, right? I'm going to show you how much they need to save the fuel, because I think people don't realize how late the engines are actually started during the flight, right? So I'm showing you one movie which you maybe have not seen before. So this is what you're going to see here is the Starship 10 falling down to Earth at free fall. It's actually 0G there. And just before it lands, it crashes, it lights up the engines. So that's a couple of 100 meters high. Right? So I think people don't realize how late into the flight they actually start this sequence of safe landing, let's call it, right? This is the most incredible thing, right? So, and they're confident that people will ride this rocket to the ground this way, right? So you can imagine how much engineering goes into this and how intense this kind of procedure is, right? So it's not easy, right? And this was the first one that actually worked, I think. Starship number 10. Okay, let's wait for it to land. Okay. Yeah, so how does Europe respond to this, right? How do Europe responds to these reusable rocket launches, right? They really lowered the price of payload going into this, putting the payload into the space. So Europe made a different bet, right? And one of the bets is they still use rockets which are not reusable, right? Ariane 6 is not reusable, but both Ariane 6 and Vega have a feature which no other rocket has, and this is the Vinci engine, which is up here, right, for the Ariane 6 in the second stage, or the Vinci is here for a Vega. And Vinci motor is actually capable of reignition, right? So and this is where bubbles again come into place, because what they want to do is they want to launch a rocket to put satellites into orbit and then reignite the Vinci engine and go into a different orbit and deliver satellites into the different orbit, and then reignite the Vinci engine to put satellites in the third orbit, right? So this is something that no other space launcher can do at this present time, right? And this is the bet of Ariane space, that this will basically sink the price for them and make it more convenient for the people to use it for delivery of satellites, right? But this reignition of the engine, this fast startup, which I was talking about, cavitation, which appears in there, this is a big issue, and this is something that is being investigated right now immensely. This is the engineering which involves bubbles in spaceflight right now. Okay, so I will stop with cavitation in space now, and I will go to a little bit different topic before I conclude, and I will go to cavitation in nature. This is a little bit towards, yeah, we can use cavitation, right? So these two guys, this is the shrimps. So this one is called mantis shrimp, and this is the pistol shrimp. They were actually using cavitation long before rockets, and they use it, as you can see here with the high-speed movie. They can use it. The mantis shrimp uses this his hand to swing against a shell, and it swings so fast that you can see bubbles appear. And these bubbles, when they implode, they crack the shell. They actually found out that the heat by the hand is actually much weaker than the implosion of the bubbles, right? So this guy is using cavitation to hunt for food, right? And similarly, the pistol shrimp actually shoots a jet of water which cavitates towards fish, for example. And these bubbles, when they implode near the fish, they would kill the fish, or at least knock it out so the shrimp can eat it, right? So nature found a way how to use cavitation, right? So, and that is, if nature can do it, can we do it, right? Can we use all this aggressiveness of bubbles which damage our turbines or pumps or rockets? Can we use that in our advantage and do something useful with it? And this is the thing that I'm working on right now. So what we do is, this is just one of the devices. It's a very simple device. This is the one I've shown you before with this small constriction. We create bubbles, and then we put into these reservoirs, we put contaminated water inside. For example, we can contaminate it with different kind of pharmaceuticals, which are really bad for the environment when they go, for example, the outflow from the hospitals. There's a lot of pharmaceuticals inside, and you want to get rid of them even before they reach the water treatment station, right? And we found out that by cavitating this water, we can actually destruct different kind of pharmaceuticals, the dangerous kind of pharmaceuticals. We also found out that we can kill, for example, different types of bacteria, like Legionella bacteria. You know that, especially in hospitals or hotels, Legionella is a big issue, right? But if we cavitate the water, we can destroy Legionella very efficiently and at a very small costs, right? And it's a similar thing with viruses. We can destroy viruses, even coronavirus. We work with coronavirus because there is a slight chance that if somebody who is sick would go to the toilet and it would flush down the drain, the water infected by coronavirus, this could re-enter the environment and infect other people. But if you cavitate it, you can really efficiently destroy this type of viruses, right? So it works. Sometimes we still don't know why it works, but it works definitely. And we are really doing a lot of very basic research on how do the bubbles interact with bacteria, how do they kill it, and so on. So I'm just showing you here one movie, which is basically a one-on-one fight between the bubble. I can show you both of them. One-on-one fight between the bubble and bacteria. And on the left one, there's an experimental one. There was a bubble here, and these rods that you see here, these are E. coli bacteria actually. And when they get permanently damaged, we call them, they light up. So these brighter ones, they actually died, and the ones that were further away, nothing happened to them, right? So we're trying to figure out this experimentally, what is important and what is not. And also we do different kinds of simulations of this would be a bacteria and this would be a bubble which collapses nearby it, and we can see what is the stress on bacteria and so on. And then we use this data, which I'm showing you here, to optimize our devices, which we use and actually implement into some kind of water system. So we have, for example, different kind of patents already for treating, well, this one is for bacteria, this one is for viruses, this one is for even dirtier water, doesn't matter. And we use this kind of devices to, first purify water, right? So we have some kind of contaminated water, and then we cavitate it by bubbles, and we get pure water out. And what else we can do is we can, if there's sludge, so sludge would be very dirty water, you can basically dry it out and you can burn it, because you cannot use that kind of sludge and manure for fertilization of fields, because there's just too many contaminants inside, too many heavy metals. But by using bubbles, you can also remove those, right? So you could use it for fertilization. So it's kind of nice. And the third thing, which is nice, you can, by doing this, bacteria likes to eat this kind of dirty water more, and it produces more biogas. So you can also produce energy with it. And you can again close the cycle, so you actually produce more energy out than you have to put in, right? So you produce more biogas later on, so the energy input for creating bubbles is relatively small. So it's kind of nice. And that's not all. Of course, we can also treat directly soil. For example, wetlands. There's a lot of heavy metals there. We can do that by bubbles. We can penetrate cells. We can put in the medicines into the cells by creating a bubble, because cells usually don't like to accept the medicine, right? But by creating a bubble, which punctures a very small hole into the cell, you can put in the medicine very, very efficiently. You can enhance chemical reactions, and of course, you can do various stuff in engineering. Okay, so this would be my last slide, more or less. And this is a reflection. Since you're mostly students here, I'm just going to show you 3 things, how my professional path was going and where it is going. So when I was, this is in Slovenia, I'm sorry. When I was in the 1st grade, so it says first grade of primary school, I wrote my first book about the moon and the sun. And this was my first contact with space. I got obsessed with space at that time, let's call it. Then 10 years later, I was still obsessed with space, and this is me on the cover of a modeling magazine, because I've made Ariane 5 rocket at that model, which actually flew and so on. And 20 years later, because I worked really, really hard, I managed to work for ESA for 7 years, right? So basically, work hard, right? It can pay off. It's not necessarily that it will. It's not the end of the story. It's still 2017. Now I'm working on completely different stuff. Like I'm working with viruses and bacteria and stuff like this. Nothing else, nothing more to do with space. But there's always new challenges. That's the important thing. But you have to follow what you want to do, but work really, really hard, right? Sometimes you also have to give up and find new goals. This is what I did in 2017. I stopped working for ESA because of different kinds of reasons. So this would be the last slide now. I'm just saying bubbly thanks. This is made by bubbles on a scale which is thinner than your hair. And I have to thank my sponsors also. This time it's the European Space Agency for this talk, and the National Agency, and the European Research Council. And of course, if you have any questions, you can also email me or Twitter me or whatever, or ask here. So thank you.
Thank you very much. It was an awesome presentation. I actually have a few questions. I am going to share my screen because I put them into a PowerPoint. Is that okay with you, or do you prefer to read them?
Yeah. No, I can stop share and we can discuss.
Okay, just. Sorry, I'm having trouble.
Or I can read them. It's okay.
Okay, so share my screen here. Oops. Okay, so it starts here.
Yeah, not the glacier. It's frozen. So if I'm climbing the glacier, I'm climbing a frozen waterfall. So this is thing that I was really into for a long time, but lately I don't climb that much anymore, unfortunately. But it's a night sport. Yeah, it's me on all three pictures. Yeah. Will it be harder to land on Mars than on Earth due to less gravity in the Starship case? I'm not sure that, I mean, it's probably Mars has lower gravity, right? So it should be easier to land on Mars in terms of fuel consumption, I would say. I'm really not an expert here. So it's somebody else would have to answer this question. But I mean, this is what they're doing basically with the big landers. They're doing the same thing, right? They're landing with the rocket engines strapped beneath them, right? And this is what they did to land on the moon. Right? The only other way to land there is by this inflatable airbags, but this is something which is only possible for very small landers like Pathfinder and so on. But the big ones which are launched by USA lately, these all need to land by rocket engines. So it's I'm thinking it's easier due to less gravity, but probably there's other problems that you have there. Collapse of the bubble in zero-G process. Yeah, process seems remarkably similar to collapse of a star. Are there parallels in these processes? Actually, there was a study also by the guys from EPFL where they compared the explosion of a bubble and the explosion of a supernova, implosion of the bubble and the implosion of the supernova. It really looks very similar, but I've talked to many astrophysicists about it, and I'm not completely sure that even they are convinced that this is the same thing. There are many things which can be parallel to this, but it's hard to say. But yes, I mean, the conditions inside the spherical bubble are really extreme. I mean, they go to such a high pressure, such a high temperature. People were even claiming that they can cause fusion reaction inside it. Right? Unfortunately, this seems not to work, so we won't have fusion reactor powered by cavitation. It's still too low. But there are many things which are similar, but not completely. But maybe we have to, whoever posed this question, maybe we could discuss this in more detail, what you meant by the question. Because there are some similarities. Okay, fourth question. So turbines can resist better to cavitation depending on the material that they're made of. What is the best one to use? That's they call it $1 million question, right? It's hard to say which material is the best. We're just learning some weird stuff going on. If you have some very soft coating of very strong material, if you would have stainless steel blade, and then coat it with a relatively soft material, something like a rubber. Then these bubbles would be repelled by this bubble. They would not implode towards the turbine. They would go away from it. And we don't really know why this happens. So it's very hard to say which material is the best one. Okay, there's a sub-question, and how this problem will be solved in order to reuse for travels to our planets to make it with. I mean, it's hard to solve. This erosion problem is hard to solve. So I know that space shuttle engines, they had to replace the pumps every time they flew. They claimed it's a completely reusable vehicle and so on, but the pumps had to be replaced at every time. SpaceX, they again claim that they are reusing it all the time, and that they don't have the problem with cavitation. But at every cavitation conference that I go to, I meet with people from SpaceX, and so they have problems with it, I guess. But I think they have a record of, I think it's called 1,000 seconds of operation. So that's 15 minutes. It can work for 15 minutes, and then it's basically done, this kind of pump. It cannot be used anymore. So I'm thinking they're also replacing this. So I'm not sure how this will be solved in any foreseeable future. I mean, it's really you could use a less aggressive type of pumping, but to do that, you would need to, for example, make your reservoir of the fuel a little bit stronger so that it would sustain more pressure inside. But if you have more pressure inside, you have to have a stronger tank, but this brings on weight. So if you have more weight, you need more fuel. So you're basically in a cycle which is impossible to get out of. This is why we are doing this on such a sharp edge, if it's possible or not. The role of Earth magnetic field to induce cavitation in rockets in outer space, is this issue considered? How much? I have no idea. I'm thinking that if you are rotating at 1,000 revolutions per second, then the magnetic field is not that important, I think. It's similar to Coriolis force, right? It's not important if you're looking at your bathtub, but if you're looking at something really, really big, such as hurricane, yeah, then it is important. But I don't think magnetic field, especially the Earth magnetic field, it should not influence it in this way, at least in a measurable way. We need a lot of pressure to create cavitation. Is it even possible to do this in such a large quantities that could be implemented in treatment plants? And how do we extract the desired biogas from the system without dropping the pressure? Okay, so what we do is actually, we have this device that we have simply said it's a very bad pump. So it's a pump which always cavitates, but we've managed to design it in a way that it doesn't get so damaged, right? So it's pumping a little bit this liquid from the wastewater treatment plant, and it's cavitating at the same time. So it basically opens up the bacteria. It kills the bacteria and it opens it up. And in treatment plants where the biogas is produced is actually it's called an anaerobic digestion. So there you have bacteria which does not, it's anaerobic bacteria which eats up all this dirty stuff. And if you pre-treat it with cavitation, then the bacteria later on likes it more and it produces more gas, right? So it's just a stage in the process. It's not a thing that you would extract biogas at the same time. It's a thing that it's like if somebody cooks a very good meal or a very bad meal. So usually the bacteria gets very bad meal, and because of that, it doesn't produce a lot of gas. And cavitation kind of spices it up so much that it likes it more and it produces more biogas at the end. So that's very, very simplified how it's done. Are there any of the cavitation tools already used? What was? Yeah, I mean, we have it implemented in a couple of water treatment plants, but it's still in the research phase for what we are doing. So we are still monitoring. There are still issues. There's issues that are really unforeseeable before, such as things that there's a lot of hair in the wastewater. There's a lot of hair, and this hair, it gets into this cavitating device and it's stuck in the rotor and makes its operation very hard. So these are the problems that we're dealing with right now. How to get rid of these very obvious problems, because bubbles work, but there's some things that are just making our lives a little bit harder. And yes, there are also many other ways and areas where cavitation is used. For example, I've shown you how to use bubbles to penetrate cells, right? This is actually used already in humans in some cases, right? So for example, one really great idea is how to bring medicines into your brain. Right? If you have a brain tumor, for example, cancerous brain tumor, it's very, very hard to treat it because brain has a so-called blood-brain barrier, which prevents anything to entering the brain because the body wants to protect it. So it's very hard to grow through this membrane. And one way to do it is just to increase the amount of medicines to a crazy level, and then some of it will actually reach the tumor. So that's not a good thing to do. The second thing is they create bubbles and they cover them with medicines, and then they make them implode, and they implode very close to this blood-brain barrier, and they penetrate it and go into the brain, right? And it actually works. And they've actually done this on humans, as far as I know, but only in cases when the patient was on the brink of will he or she survive or not. In this case, they would use this kind of treatment, more as experimental treatment that maybe it will save this person's life. Well, so this is stuff that is already implemented, let's call it like this. So there's a lot of research done in that field. Yeah. Last question. Is corrosion made by cavitation in devices that use cavitation? Yeah, there is problem with cavitation also in those devices, but it's not too bad. I mean, we've had devices work 24 hours per day for months, and we've seen damage, but it was not so bad. They still don't work at the rates as rocket inducers work, right? So it's not so bad. So we can work for months or years even without any problems. And then after that, maybe we should replace a part or so on, but that's not an impossibly high price to do that. So right now, we don't see it as a problem.
Okay, well, if you guys have another question, you can just write it or talk if you want. Otherwise, thank you so much for doing this. It was a very interesting webinar. I learned a lot. This is absolutely not my field, so I loved it.
Thank you.
And yeah, I think that's pretty much it.
Okay, thank you for the invitation. It was a pleasure.
Thank you, and see you soon.